All right, Chapter 13 is about solutions. How does the lattice energy of an ionic solid affect the solubility in water? All right, so as we got to in Chapter 12, it takes energy to expand the solute. So the stronger the lattice energy, right, the stronger the attraction between the cations and the anions, the harder it's going to be to separate the ions. So you're going to have a more endothermic heat of solution if you have to put a lot of energy to expand the solute because of strong ion-ion attractions. 5. Which of the following best represents a saturated solution? Explain your reasoning. All right, a saturated solution is when you can't get any more solute to dissolve in the solvent. So at this point, you start building up solid on the bottom. So that looks like B to me. At this point, you've saturated the solution. Any more solute going in there is just surrounding each other as a crystal on the bottom of the beaker. So you end up with an equilibrium being established, a rate of escape into the solution phase equal to a rate of return. And that's as much solute as you can get into the solvent. Number 6, the solubility of xenon in water at 1 atmosphere and 20 degrees Celsius is approximately 5 times 10 to the minus 3 molar. Compare this with the solubilities of argon and krypton in water. And explain what properties of the rare gas atoms account for the variation in solubility. Oh, I didn't take into consideration the table, but what I'm saying is argon and krypton must be less soluble because they're less polarizable. The smaller the atoms, the less polarizable they are. All 3 of these are nonpolar. But xenon's big and puffy, all right? So you can warp the cloud easier and get an attraction between the water and the gas more than you can the argon and the krypton. So I'd say argon would have the lowest solubility in water because it's the least polarizable. Xenon would be the most soluble in water because it's the most polarizable. The structures of vitamin E and B6 are shown below. Predict which is largely water soluble and which is largely fat soluble. Explain. Okay. Well, these are the molecules, all right? And if I'm looking at B6, I don't see a lot of big nonpolar chains here. And I see OH groups that are capable of hydrogen bonding. So B6 is going to be more soluble because it's capable of hydrogen bonding with all these OH groups. Yeah, you have an OH group on vitamin E, but you've got this whole big nonpolar section to it, right? That's all nonpolar. Those carbon-hydrogen sp3 hybridized carbons are nonpolar. So all you have there are dispersion forces. So that'll be fat soluble, whereas it won't be water soluble. The only hydrogen bonding potential is this one OH group down here. Vitamin E would be more fat soluble due to a long nonpolar hydrocarbon. The following diagram shows the vapor pressure curves of a volatile solvent and a solution of that solvent containing a non-volatile solute. Okay, which line represents the solution? The blue line represents the solution with a lower vapor pressure at a given temperature. Right? So if I follow the line 50 up, I hit the blue line at a lower vapor pressure. So the question is why? Why is the vapor pressure lower when you have this solute dissolved in the volatile solvent? Well, this is the way it works. All right. First of all, vapor pressure. What is vapor pressure? At any given temperature, a certain number of solid particles have enough kinetic energy to escape into the gas phase. So at a particular temperature, say 50 degrees Celsius, a certain number of those particles can escape into the gas phase. That's what vapor pressure is, the amount of particles sitting up over the liquid in the gas phase. All right, if I put a non-volatile solute into this solvent, something like sugar, which doesn't have vapor pressure, the sugar breaks apart and it occupies surface sites, which doesn't allow the solvent to be there, right? So if you got a sugar at the surface site, there's no solvent there. Therefore, the solvent can't escape into the gas phase. So by putting the non-volatile solute into the solvent, you lower the vapor pressure. Less particles escape into the gas phase. So the rate of return is the same, but the rate of escape is different. So you end up with a lower vapor pressure. This is why the blue line represents the solution with the non-volatile solute in it. All right, B. What are the normal boiling points of the solvent in the solution? All right, so normal is 1 atmosphere. So if we follow the line across, right, at 1 atmosphere, we hit the red line at about, I don't know, what is that, like 65, 64 degrees Celsius. So if you're talking about boiling point, right, the point at which the substance goes into the gas phase, right, at a particular pressure, right, I mean, that's any point along that red line. So at 1 atmosphere, normal boiling point for this substance would be about 64 degrees Celsius. For the blue line, it's higher. So when you put a solute into a solvent, you make it harder to boil, all right? You lower the vapor pressure, less opportunity to get into the gas phase, and therefore it's harder to boil. You got to get the temperature higher to get around those obstructions. So boiling point elevation, vapor pressure lowering. This is what happens when you put a non-volatile solute in a solvent. All right, 15. Indicate the type of solute-solvent interaction that should be most important in each of the following solutions. Tetrachloromethane in benzene, methanol in water, potassium chloride in water, and hydrogen chloride in acrylonitrile. All right, so with A, tetrachloromethane is nonpolar, benzene is nonpolar, so all you're left with is dispersion forces, induced dipole attractions. Methanol has an OH group, water has an OH group, so hydrogen bonding would be the primary thing that would, the primary interaction between the solute and the solvent. And potassium bromide is an ionic compound, so when you put it in water, you get ion dipole interactions. Hydrogen chloride is a polar molecule. Acrylonitrile is a polar molecule. So you get a run-of-the-mill dipole-dipole interaction between acrylonitrile and hydrogen chloride. 20. The schematic diagram of a solution process is the net sum of 3 steps. In figure 13.4, does not show the negative magnitudes. It does not show the relative magnitudes of these 3 components because these will vary from case to case. For the dissolution of lithium chloride in water, the heat of solution is exothermic, right? Negative 37 kilojoules per mole. So which of these three enthalpy changes would you expect to be more negative than the other 2? Explain. All right. In order to dissolve something, you have to expand the solute, you have to expand the solvent, and then you get a release when they mix. So endothermic to expand the solvent, endothermic to expand the solute, and putting the 2 things together, you get an attraction between them, which is either releases more energy than you put in or not. If it releases more energy than you put in, it's going to be an exothermic process or an exothermic heat of solution. If it's less than the energy put in, then it's going to be an endothermic heat of solution, right? You had to put more energy in than was released. So if the heat of solution is negative, the heat of mixing, delta H3, must be more negative than the heat to expand the solute and expand the solvent. So I add the 3 heats together to figure out what the heat of solution is going to be. Expand the solute, expand the solvent, heat release when I mix. So heat release when you mix is the exothermic one. When 2 nonpolar organic liquids like hexane and heptane mix, the enthalpy change is generally quite small. All right, use the enthalpy diagram in figure 13.4 to explain why. B, given that the heat of solution is close to 0, explain then why heptane dissolves so readily in hexane dissolves so readily in heptane. All right, you'd have to put heat in to expand the solute. You'd have to put heat in to expand the solvent, right? Expand the hexane, expand the heptane. You get a release when the hexane and heptane come together. Point is when you add up the heats put in and the heat released, they're about the same. So what drives this forward? And again, they're about the same because it's weak, right? Weak, low energy to expand, low energy to expand, very little energy released when you mix. So what drives this reaction forward is the fact that you're becoming more disordered. And later on in the course, we'll get into this in more depth, but it's called entropy. And systems are more spontaneous when they are more disordered at the end. And that's what's going on here. A more disordered system is a more likely outcome. And this is why hexane will mix so readily with heptane, because you're becoming more disordered at the end. So it's the two things that go into whether things happen or not. What's the heat change, and are you becoming more disordered? (25) By referring to figure 13.8, determine whether the addition of 40 grams of each of the following ionic solids and 100 grams of water at 40 degrees Celsius will lead to a saturated solution. A saturated solution is one where you can't put any more of the solute in the solvent. And that's what it means. It means you can't put any more in. So what this chart shows is how soluble, right, a certain number of grams, 100 grams of water, each of these ionic solids is going to be at a particular temperature. So our temperature, our grams, falls here on the chart. So if you're on the line anywhere on this chart, that represents a saturated solution. So if I'm looking at potassium chloride, that looks like it's just above the line. It looks like I could get as many as maybe 39 grams of potassium chloride to dissolve at 40 degrees Celsius. After that, my last gram just falls on the bottom of the beaker. I've hit my saturation point. I can't put any more potassium chloride in the water. If I'm looking at lead nitrate, at 40 degrees Celsius, I could put as many as, 73 grams of lead nitrate in the water and still be able to put a little bit more in. As long as I'm below the line, I have an unsaturated solution. This graph also shows that saturation is dependent on temperature. Change the temperature, change the saturation. So, or the solubility, I should say. So most of them, right, increase. I can get more of the solute to dissolve in water at a higher temperature. The one that goes against this is the cesium sulfate. As I increase the temperature, it gets less soluble. So, solubility changes with temperature. Water and glycerol are miscible in all proportions. What does this mean? Miscible means I can dissolve as much of the solute in the solvent as I want. I never hit a saturation point. How do the OH groups in alcohol of the alcohol molecule contribute to the miscibility? Well, you're going to be soluble in something that's like you, or I should say like the solute, the solvent. So this means that if I'm capable of hydrogen bonding, I'll be soluble in a solvent that can also hydrogen bond. So glycerol has a whole bunch of OH groups on it. All right, this is what makes it soluble in water. It's capable of hydrogen bonding with the water. So the term is like dissolves like. Right? If I'm capable of, if the solvent is capable of hydrogen bonding, things that'll hydrogen bond will be soluble in it.